Hello folks, we're back with more integrals. Today we're going to do cylindrical and spherical coordinates and, we're going to try to do integration with respect to cylindrical and spherical coordinates. So the idea with the cylindrical integration, we're going to start with cylindrical coordinates, is let's say you have three-dimensional shape like this. It's like an ellipsoid. It's like a American football ball. Okay. So we'd like to integrate this, and we saw last time when we were doing triple integrals how we would set these integrals up in rectangular coordinates. Now remember, we were basically integrating the heights, okay, where you go into the solid and where you're going to come out of the solid with respect to the z-axis, okay, the heights, over the region R, where the region R was basically the projection, the shadow of this ellipsoid on the xy plane, okay. So we set that integral in rectangular coordinates as basically whatever this function. Maybe we're integrating the density function, or maybe we're trying to find inertia, or maybe we're trying to find the centroid. We're integrating some kind of function f continuous over the solid over this guy. If we were just trying to find the volume, we would just do dv. We wouldn't do any function in there. Now, how did this work out? Again, the way this worked out is basically we did the heights, okay, and from where it entered and where it left, and these would be usually in terms of just x and y, a function of x and y. Z would be a function x and y, and we would integrate that over the two-dimensional region, which is the projection on the xy plane. Now, we've seen some examples where when we got to this step, when we did the first integral and we got to this step, R was really hard in terms of rectangular coordinates, and we did polar substitution. The idea with cylindrical coordinates is, before we get to step, let's just set it up so that we can go straight to basically this step and then polar substitution. That's called cylindrical coordinates. The idea with cylindrical coordinates is, again, we're going to represent every point, but this time we're going to represent, in polar coordinates, we represented points on the plane in terms of polar coordinates. This time we want to represent points in three space. So three points with three coordinates, x, y, z. These would be the rectangular coordinates, and we want to send them to x equals r cosine theta, y equals r sine theta, and z equals z. Don't mess with the height. Z stays the same. So basically this part of it is just the polar substitution. So if you look at a picture here that I try to draw, if this is the point that we're trying to represent, we're going to represent it in terms of r, theta, and z, where r and theta are just basically its polar coordinates on the xy plane, okay, of its projection, okay. So you get the xy coordinates, and you look at on the plane what its polar coordinates would be, and just keep the z the same, okay. So basically you're making a circle and you're just pulling it up. So that's why it's called cylindrical coordinates. Again, the transformation from rectangular coordinates to cylindrical coordinates are very easy. The first two ones are just the polar transform, and z stays the same. Okay. So under those conditions, how would a rectangular integral look like? Okay. So remember, we were trying to integrate this. This was like a ellipsoid kind of region over, and a function over that region. So that would turn into, we said, that would turn into this if we were doing it normally. But instead, if we're trying to do it in terms of cylindrical coordinates, now I have to write this function z1 and z2 in terms of polar coordinates. Now they're just in terms of x and y, so they're going to be polar coordinates. So I call this big function z1 as the representation of small z1 in polar coordinates. Similarly for z2, big z2 is the polar representation of the z2 function, the small z2 function. And this s is basically the polar representation of this region R. We say this. We've done examples, remember, of this in triple integrals. So if the cylindrical representation of t, is u, okay, the integral is going to turn into if r cosine theta, r sine theta, z, where this f, oh sorry, this is big F. Oh, so sorry, this small f is basically xy, f of x, y, z, but instead of x was r cosine theta, y was r sine theta, z was z. And because we just basically made the polar substitution in the two-dimensional projection, that part of is r dr d theta, and we didn't do anything with the z, so that's going to stay dz. Okay. So again, I don't know if this does you much good, but we're going to see some examples on how to apply this formula. I'm also going to get this through the Jacobian. We haven't done a 3x3 Jacobian, so I wanted to do a 3-variable Jacobian. We're going to do it in a minute. All right. So let's try to do the Jacobian and really see that this dz, dy, dx really does go to r dz dr d theta. Okay. I mean, from the way we set it up, it looks like that's supposed to make sense. But let's just make sure. So remember, our transformation was x equals r cosine theta, y equals r sine theta, z equals z. So the Jacobian for this 3x3 is going to be x sub r, x sub theta, x sub z, y sub r, y sub theta, y sub z, z sub r, z sub theta, and finally derivative of z with respect to z. Now, obviously, let me just make a comment here. Obviously, derivative of z with respect to z is just 1, so that's why you get 1 here in the determinant. Okay. And since z is an independent variable, it's not dependent on x, y, and z, the derivative of x with respect to d and y with respect to z are going to be 0 because there is no z in x and there is no y there is no z in y. Yeah. And similarly, there is no x in z and there is no y in z, so these are going to be 0, 0. So basically, the derivatives are going to come from here, right? These are just the polar derivatives, the polar Jacobian that we had. And you take the determinant of it, and of course the determinant is now going to be r, okay? Which is not surprising. Basically, it's the polar determinant, okay? And we're basically expanding that determinant on 3, 3, okay? So yeah, you're going to multiply it by 1 here. Okay. So it's basically the same. So it's basically the same thing as the polar one, r dr d theta, but we have the third variable dz, which didn't get changed at all. So it's r dr d theta, dz dr d theta. Some books like to say this is dz r dr d theta. It doesn't matter. This way is a little simple. Now I wanted to make some show you some examples of what cylindrical functions look like. A cylinder function is, remember, going to be of the form r theta z. So I want to show you constant ones in all of them. So if r is constant, that means theta can go from anywhere. So you're going to get a circle on the bottom, and z can go up anyway. So you're basically going to get the circle. If r is equal to a, you're going to get the circle with radius a, but that's going to be, because you can go up as much as you want, that's going to be a cylinder with radius a. Okay, it's an infinite cylinder. It goes up as much as you want, goes down as much as you want. Okay, what about if theta stays the constant, theta equals alpha? Well, that means you're going to get a half plane, right? So the angle from the x-axis, positive x-axis, towards the y-axis counterclockwise is alpha, and you can go out as much as you want. R is free, and z is free, so that's going to be a half plane. Okay, and if we keep z constant, that means the angle and the distance can vary, but z has to be the same. So it's basically the plane that intersects at z naught. That's what you get. Okay. So you can play around with these, see the cylindrical representation of functions of 3 variables. But we're not going to spend that much time on it. I want to jump into integrals straight away. Okay. So the first one that we're going to do is we want to find the volume of the solid bounded by the paraboloid z equals a times x squared plus y squared, where a is a positive constant. And it's bounded above by z equals b, where b is, so we're looking at the paraboloid. Basically, paraboloid is coming out towards you, and we cut it off at the height b. Okay. So I try to draw this. So the paraboloid looks like this. We're cutting it off at the height b. We want to find the volume of this 3-dimensional shape. Okay. So if you look at the two-dimensional version of it, it's gonna look like this. From the side, it's gonna look like this, and this height here is b. Okay, so we want to calculate the volume of this. Now we need the projection of it, so I tried to draw the projection of it. Basically, when you look at the paraboloid, the projection of it is going to be, because it's expanding like this, it's going to be the top. The very top is going to have the largest radius because it's expanding like this. Okay, it's expanding. The very top is going to have the largest radius. So the projection on the xy plane, the region that we're trying to integrate, I tried to draw a circle below the paraboloid, unsuccessfully, unfortunately. So the largest circle is going to be when z equals b, and where do these guys intersect, the paraboloid and b? Well, when z is equal to, b is equal to this constant, right? Now, the polar representation of x squared plus y squared is r squared, so this gives me b equals ar squared, and solve for r, we get r is equal to square root of b over a. So basically, when we're talking about the region here, okay, so this distance here is basically square root of b over a. Okay, so which means when we're talking about this on the projection on the xy plane, the radius of that thing is also going to be r. The radius is going to be square root of b over a of the projection of the paraboloid from the top. Okay. So if I wanted to set the integral up over this solid, I want to find the volume. So that would be over this solid t. We're just going to do dv. And we do this in cylindrical coordinates now. Now let's look at the heights. The heights are going to go from the paraboloid on top, on the bottom, all the way up to the plane z equals b. From the paraboloid, this is the paraboloid. It looks like a parabola, of course, two-dimensional when we look at it at the side. So it goes from the paraboloid all the way up to z equals b. What was the paraboloid? The paraboloid was a times x squared plus y squared, but x squared plus y squared in polar coordinates was r squared. So it's going to go from the paraboloid z equals ar squared to all the way up to z equals b. Okay, and we said the radius is going to be from 0 to r equals square root of b over a. And of course, you're going to go all around, so that's going to be 0 equals to 2 pi. Okay, so the inside the integral, we have dv turns into r dz dr d theta. And just as an example, again, what's important for these problems for you guys is to be able to set it up correctly. Then, of course, integrating is basically the engineering part of it, okay? The quant part of it. But it's very important that we get the setup correct. I solved this integral. We're not going to do all of them. I'm not going to solve all of them, but I'm going to set them up usually. I solved this so we could see an example of how this would happen. Of course, the integral of 1 with respect to z, or the integral of r with respect to dz is rz, okay? From ar squared to b. Plug it in, you're going to get rb minus r cubed a. And we'll integrate with respect to r now, you're going to get r squared over 2. B minus r to the 4a over 4. Okay, and that's going to be, the second limits were from 0 to square root of b over a. I plugged it in, you get this, and then integrate it with respect to theta, plug in 2 pi, and lo and behold, we get pi over 2 b squared a. That's going to be the volume. Okay, so this was a cylindrical example. Now, of course, you want to do cylindrical integrals and spherical integrals also. We haven't done spherical yet. We're going to do that in a few minutes. You want to do cylindrical and spherical integrals when your solid has a lot of circular symmetry. Okay. So what I wanted to do was I wanted to do the volume of a sphere again. This time let's set it up with respect to cylindrical coordinates. So we're going to take the sphere, x squared plus y squared plus z squared equals c squared. Remember, this is the sphere centered at the origin with radius c. I'm not using the letter r, not to confuse it with the variable r, okay? So if I say the radius is r, then r is constant, but if I say r is a variable, then r becomes a variable. So you don't want that confusion, so I'm going to say it's equal, the radius is equal to c, okay? So the first thing I'm going to try to do is, again, we're going to do the heights. We're going to integrate over this region. We're going to do all the heights. So what are the heights going to be? What's the top half of the sphere and the bottom half of the sphere in terms of x and y? Well, they would be through x squared, y squared to the other side. You get z squared is equal to c squared minus x squared plus y squared. Of course, this, as we know in polar coordinates, is r squared. So we get the formula, take the square root, you get z equals plus or minus square root of c squared minus r squared, okay? Okay, so, and what about the two-dimensional projection of the sphere? Well, the two-dimensional projection of the sphere, what's the fattest part of the sphere? It's the equator, right? So it's the projection of the equator on the xy plane. Well, what's the equator? It's the circle r equals c, right? Because it's got radius c, okay? So z top minus z bottom, z top is the positive part. The top half is the positive square root. The bottom half is the negative square root. We're going to do r equals 0 all the way to r equals c. And as usual, because we're doing the whole sphere, we're going to go all around 0 to 2 pi. And we're going to do r dz dr d theta. Okay? So I did this one. This is going to, because this is supposed to be easier than the rectangular version of it. So what's going to happen here is we're going to go from r equals 0 to r equals c. I did the first integral. The first integral is, of course, going to be, it's in terms of z, so you get rz. Now plug in z this minus z this, so we're going to get two of these guys, okay? So the integral is actually rz. The integral is rz. Plug it in, you get r square root, minus r minus square root. So you're going to get two of these. The minus is going to make it a plus. You're going to get two of these guys. So that's why the next integral is twice the square root times r dr d theta. Now this integral was supposed to be easy. You might say, hey, it looks horrible. It doesn't. You don't need to do trigonometric substitution or anything like that. Normal substitution is going to be perfectly fine here. If you call u equals c squared minus r squared, the inside of the square root, I realize that I really have something close to du here, right? Minus 2r dr. I have 2r dr. So this is basically minus du. The only thing here is we have to change the limits of integration because the limits of integration are given with respect to r. If we're going to write u now, this is going to be square root of u. We have a minus because of this minus sign, okay? But now we have to change the limits of integration to u. So when r is equal to 0, u is equal to c squared minus r squared, so u is going to be equal to c squared. So it's going to start from u equals c squared, and when r is equal to c, u is going to be equal to, of course, 0, okay? So we have this integral, the minus of the square root, from u equals c squared to u equals 0, du d theta, okay? Integrated, this is u to the 1/2. Integrated, add 1, you have u to the 3/2. Divide by 3/2, that's the same thing as 2/3. Okay, multiplying by 2/3, dividing by 3/2 is the same thing as multiplying by 2/3. And we had this minus sign, don't forget the minus sign. So now we have to do the d theta from 0 to 2 pi. And you integrate that, basically, we're going to get, hold on, sorry, u to the 3/2, sorry, we didn't evaluate it yet. Yeah, it's c squared to 0. So plug that in, we get 2/3 c cubed d theta. And from 0 to theta, it's going to be 2/3 c cubed theta. Multiplied by 2 pi, you're going to get 4 pi c cubed over 3, which is the formula that we've known since elementary school, right? It's the volume of a sphere. Okay, so that worked out fine. Let's do a harder example. So here's our question. Find the volume of the solid bounded below by the plane z equals 0. That's the xy plane. Laterally by the cylinder. So on the bottom you have the plane. It's going up. The cylinder is going up like this. But it's bounded on top by the paraboloid z equals x squared plus y squared. So I tried to draw the picture, two-dimensional picture looking from the side. So this is the zy. This is the zy axis. The cylinder looks like a rectangle going up. Okay, so the cylinder is coming up towards you, but we're bounding it with a paraboloid. Okay, so we have to hollow out the paraboloid. So the paraboloid is hollowed out, and on the outside you got the z, the cylinder x squared plus y squared equals 1, and on the bottom we get the z equals 0. So if you do the heights from here, the heights are going to go from from 0 all the way up to paraboloid. Okay, so that's going to be our height. Well, what's the paraboloid? The paraboloid is basically, since it was x squared plus y squared, that's just r squared, right? So the heights are going from z equals 0 to r squared. Z equals 0 to r squared. That's what the heights are going. And the radius of the circle, well, we're integrating over the cylinder. The bottom of the cylinder is, of course, the circle x squared plus y squared equals 1. So the radius is 1, 0 to 1. And again, we're doing it 0 to 2 pi. I didn't do the math here. Okay, the setup was more important. The math, if you do the math, it comes out to pi over 2, I think. All right. Now, that's enough examples. That's enough examples for cylindrical coordinates. If you look at any calculus book, you're going to see lots of examples, especially in the problem section. So I would suggest you, again, spend some time looking at those sorts of questions. When somebody, when a professor is doing these, it looks easy, but when you try to do them yourself, you get confused. Again, you would only want to do the cylindrical substitution, the cylindrical coordinates, integration with respect to cylindrical coordinates, when you have solid that is very has a lot of circular symmetry. Basically, you wouldn't want to do something that's got corners, or that's not nice circular, that's not, it's basically, it looks rectangular. You wouldn't want to do cylindrical coordinates. It would just make your job harder. So another thing that we can do, another substitution method that we can do, is we can represent stuff in spherical coordinates. Now, I'd like to say a word of caution here. Remember, I just said you'd like to do cylindrical coordinates when stuff has lots of circular symmetry. So the same goes for spherical coordinates, but three-dimensional objects don't have spherical symmetry. The only three-dimensional object that has spherical symmetry is the sphere itself. So the spherical integration method is really usually becomes a lot more handy if you're trying to do four-dimensional, not triple integrals, but four integrals, quadruple integrals, I guess. It would be really useful. It's usually not useful on three-dimensional objects if the object is not a sphere. Well, if the object is a sphere, you know what you're doing anyways, right? But it's a method that you have to learn, because on higher coordinates, basically the spherical one replaces the cylindrical one in higher coordinates. Let's try to do this in 3 dimensions and see what happens. Basically, what we're going to try to do is we're going to try to represent every point in the 3-dimensional space in terms of its spherical coordinates. What are the spherical coordinates? Basically, what we're trying to do is we're trying to take x, y, z, a point x, y, z, and we would like to write it in terms of its distance r on the, its distance rho from the origin. And we have to determine it. We're going to use 2 angles. So let me try to show this with my pen. Let's say we're interested in the tip of my pen here. Okay, that point in the 3-dimensional space. Now, how would I try to do that? Well, I would need, first of all, the length of this pen. That's going to be rho. That's different from r. We use 3-dimensional distance. When we're talking about 3-dimensional distance from the origin, we say rho. When we're talking about 2-dimensional distance from the origin, distance in the xy plane, we use the letter r. Okay, 2 different things. If it's in the plane, the distance from the origin is going to be r. If it's in 3-dimensional space, the distance from the origin is rho. So I would need this distance from the origin, and well, it can turn around, it can go anywhere, right? I need 2 angles. Basically, I need this angle. How much do I turn it on the xy plane, and how much am I going to turn it from the positive z-axis? Okay, so the amount that I'm going to turn it, I'm going to say we're talking about this. Let me put my finger. Hold on, guys. This is not going to work out. Let me get an orange. I'll be right back. I'll show it to you on the orange. Okay, so I'm back. I got an orange, so we can actually show this. Okay, so basically the xy plane is the paper, and the z plane is coming to the z-axis is coming towards you guys. Okay, so it's kind of like the top. Let's draw a point here. Let's draw a big point here on the orange. Let's say I want to represent that point. Okay, so the first thing I need to do is I need to find its distance, And the second thing is I need to decide on two angles. The first angle is, well, how much do I go from the positive z-axis this way towards the xy plane? Well, I'm going to go this much. And then how much do I turn it on the xy plane? And it's going to be this much, okay? So think about my pen. My pen is sitting right here. I have to turn my pen like this and then rotate it like this, okay? Or in other words, rotate the pen like this. So the amount that I'm going to do the rotation on the xy plane, this horizontal rotation, okay, this horizontal rotation, how much do I need to rotate from here, from the x-axis? Here's the x-axis, here's the y-axis, okay, x, y, okay. So I would basically need to rotate all the way up here, okay. This angle is going to be theta, okay, and the amount that I need to do from the positive, so this angle here, that would be phi. This would be phi, this would be theta, okay. So let's go back to my horrible picture. So the amount that you would need to rotate from the positive x-axis is theta, and the amount that you would need to rotate from the positive z-axis downwards is called, that angle is called phi. Now, we're going to represent, so we have rho, we have phi, we have theta, in that order, rho, phi, theta, okay? So how are we going to do the representation? Let's look at the transformation of this. How is this going to go from x, y, z to rho, phi, theta? Okay, so a word of warning here. My rho's, this is the Greek letter rho, my rho's, of course, look a lot like p. So don't be like me. Don't say, don't write p, and then your phi might look like a p also. I mean, it becomes worse and worse. So let's try to do, I'm going to try to do rho's like a p. Hopefully when you're a professor, you don't do it that way and your students won't get confused. So p is rho basically. Okay, so let's do the transform. Let's see how we're going to transform this. So I try to draw a cleaner picture here for you to see. So we're interested in this point here. This is the point that we're interested in. So basically, let's talk about the x-coordinate. Well, the x-coordinate is going to be basically the projection of this onto the y-plane, okay? So the distance r is going to be the projection of rho onto the xy plane. Well, what's that going to be? Well, if you look at this angle was phi, so this thing and this thing are the same, okay? This side, it's a parallelogram. This side and this side is the same. It's a rectangle, basically, not a parallelogram. This side and this side is the same. So what would this side be? That would be sine theta. So r is equal to rho sine theta. So x was, remember, equal to r cosine theta, but r itself is rho sine theta. Plug it in, so we get x is equal to rho sine theta cosine theta. And y was r sine theta. Again, plug in r is equal to rho sine phi, so you get y is equal to rho sine phi sine theta. And z is equal to rho cosine phi. I mean, you don't want to keep drawing this figure all the time. I suggest, you should know how to do this, but I highly suggest you remember this transformation, you memorize it, okay? This transformation, r equals rho sine phi, is also important. Now, once we have the transformation, of course, we have to talk about this Jacobian, because we're interested in spherical coordinates with respect to integration. So what would the Jacobian rho phi theta be? Well, again, you set it up, the partial of x with respect to rho, the partial of x with respect to phi, the partial of x with respect to theta, and ditto for the other variables. So I did these, I calculated, it takes a little while to do this one, but it really does clear out, it simplifies. So the partial of x with respect to rho would just be sine phi cosine theta. The partial of x with respect to phi would be, this would be cosine phi, so it's going to be rho cosine phi cosine theta. And the partial of x with respect to theta was cosine theta, the derivative of that is going to be minus sine theta, so it's going to be minus rho sine phi sine theta. Okay, so I wrote all that here. Similarly, you do the same thing for y. Z is, of course, a little bit easier. The partial of z with respect to rho is just going to be cosine phi, and the partial of z with respect to phi is going to be minus rho sine phi. Okay, so we're talking about the determinant of this 3 by 3 matrix. Okay, we have sine phi across this diagonal, it's 0. here you have a rho squared, cosine phi, sine phi, cosine phi. So cosine squared sine phi times cosine, that's going to be cosine squared theta. And you go across this one, minus and minus is going to make it a positive. You're going to get rho squared sine phi, sine cubed phi, and sine squared theta. Okay. Now we go this way. Of course, these guys are going to be, the backwards diagonals are going to be minus. So it's going to make this a plus. You're going to get a rho squared. Okay. And you have a sine phi, cosine phi. So that's going to be cosine squared phi, sine phi, times you have a sine squared theta. Okay. And now if we do this one is 0. So let's go on to the third one. This one is going to be, again, minus and minus is going to make it a positive. That's going to be rho squared, sine cubed, cosine squared. So sine cubed phi, cosine squared phi. So now this is going to clear out really, really nicely, because if you notice, these terms are the same. There's a cosine squared at the end. There's a sine squared at the end. So that's a 1 when we factor out these terms. So this is just going to be basically rho squared, cosine squared, sine phi when I do these two terms, okay? So that's what we're going to get, rho squared, cosine squared, sine phi. Similarly, these two terms, if I factor out rho squared, sine cubed squared, here I'm going to have sine cubed, here I'm going to have cosine squared, sine squared, cosine squared, that's going to be 1. So these terms are going to simplify out to rho sine cubed, basically, rho sine cubed. No cosine squared, it's just rho sine cubed. Okay. So rho sine cubed, rho squared sine cubed. Now let me just do one more step. I'm going to do sine cubed as sine squared times sine. So we have rho cosine squared sine theta, rho sine squared sine theta. So that's just going to be rho squared sine. Okay. So dz dy dx is going to change to rho squared sine phi. That's the Jacobian, rho squared sine phi d rho d phi d theta. Okay, let's see an example. Oh, before we see an example, let's see how these functions would look like when each variable is constant. Okay, when rho is constant, we have spherical coordinates functions look like f of rho phi theta. When rho is constant, basically c, that means your distance from the origin is constant, so you have a sphere with radius c. Now, if phi is constant, that means the angle from the positive z-axis, you always go down like this, is constant. Let's call it gamma. So the angle from the positive z-axis is constant. So if it's constant and r is free and theta is free, right? That's going to give you a cone. Similarly, let's do theta is equal to alpha. Well, the positive angle from the x-axis is constant. That's going to give you a half plane just like we had in cylindrical coordinates. Now, I want to give you a word of caution here. When we're talking about three-dimensional objects with respect to spherical coordinates, theta, well, you can turn it around like this. Theta is going to be between 0 and 2 pi usually, but phi, the amount that you turn from the positive z-axis is going to be between 0 and pi. And why not 2 pi? People get confused. Why not 2 pi? So just think about this point here, right? Well, I can get to this point by going some angle less than 90 degrees, right? If we talk about points here, right? If we talk about a point here, I would almost need to go 180 degrees down here. From the phi would need to go 180 degrees down here this way. Now you might say, what's going to happen if the point is right about here? Don't you have to go all around? Okay, roll this all around. Don't you have to almost go 2 pi? And the answer is no. What you do is you rotate it first with respect to theta, and then you have to do a very small angle, right? Less than pi. So again, let me show you this. If your angle was here, phi would be very small, okay? And you might think I might need to go all the way around if I'm talking about this angle, this point here, almost 2 pi. But the answer is no. You rotate the theta and then go like this, okay? So phi is usually bounded between 0 and pi, okay? That's important to keep in mind, that when you're talking about these objects with lots of circular symmetry, theta is usually going to be between 2 pi and 0 if you're going all the way around, and phi is going to be between 0 and pi. Okay. Okay, so let's again try to do the volume of the sphere with respect to spherical coordinates. I mean, hopefully, volume of the sphere with respect to spherical coordinates is going to be very easy to do. And that's what we're going to do. Again, the sphere we're going to look at is x squared plus y squared plus z squared equals c squared. So obviously, the distance is c. The rho goes from 0 to c. Phi goes from, as I said, 0 to pi. And theta goes from 0 to 2 pi. And you just put in your Jacobian. Here's my Jacobian. And the rest is d rho, d phi, d theta. And while integrated with respect to rho, you're going to get rho cubed over 3. Plug in c, you're going to get c cubed over 3 sine phi d theta d phi d theta. Integrate with respect to d phi now, you're going to get minus cosine phi, right? C cubed minus cosine phi. Evaluate from 0 to pi. When you plug it in, you get 2 c cubed over 3. 0 to 2 pi d theta. That's going to give you, again, 4 pi over 3 c cubed. Notice that this was shorter than the cylindrical version, okay? This was a little shorter than the cylindrical version. Of course, that's when you know the Jacobian. You have to memorize this Jacobian, guys, okay? Okay, you have to memorize how, if you have that memorized, it's much shorter. The only thing that's confusing here, you have to be careful with the minus sign when you plug in 0 to pi, okay? Plug in pi, minus a minus makes it a plus, and plug in 0, minus a minus again makes it a plus. So you get 2 of those, 2c cubed over 3. Okay, so let's do a harder example. Let's go back to our paraboloid and cylinder problem. Remember, we just did that in terms of cylindrical coordinates. In terms of cylindrical coordinates, this is going to be a little harder. This is going to be a little harder when you're doing it in spherical coordinates, because a cylinder and a paraboloid don't have spherical symmetry. They have circular symmetry. They don't have spherical symmetry. So unfortunately, this is going to be harder. The reason you got to learn it is, well, you need to be able to do these substitutions when you have more variables. So again, we're talking about the paraboloid bounded below by the xy plane, z equals 0. The cylinder bounded below by the xy plane. It's x squared plus y squared equals 1 is our cylinder. So it's a cylinder with radius 1. It goes up like this towards you guys. And it's bounded above by the paraboloid. So again, I drew this on the zy axis, just looking at the side picture of it. Okay, this is the y, this is the z axis. On the side picture, the cylinder looks like a rectangle, right? And the paraboloid is carved out of it. Okay, so this is the paraboloid. Okay. So now we have to, unfortunately, we have to now get everything in terms of spherical coordinates. We have to get the paraboloid in terms of spherical coordinates, and we have to get the cylinder in terms of the cylindrical coordinates. Let's start with the cylinder, because that's going to be a little easier. So the cylinder has the equation x squared plus y squared equals 1. So that's basically r squared equals 1. But remember, r was equal to, we did that just a few minutes ago, r was equal to r rho sine phi. So r squared equals 1 means rho squared sine squared phi is equal to 1. So I'm trying to get this in terms of rho. So we have rho squared is equal to 1 over sine squared phi. And basically take the square root. You're going to get rho is equal to 1 over sine phi. In other words, rho is equal to cosecant phi. Okay, so that's the cylinder. That's the equation of our cylinder. X squared plus y squared equals 1 in terms of spherical coordinates. Now let's go on to the paraboloid. That was z equals x squared plus y squared. So that's of course going to be z equals r squared. Again, z itself, remember, is rho equals cosine phi, and r was rho sine phi. So this is going to be z equals rho cosine phi equals r squared, rho cosine phi equals rho squared sine squared phi, okay? Because r was equal to rho sine phi. So now this is going to be a little bit more interesting to solve. Let me throw this to the other side. So I have rho squared sine squared minus rho cosine is equal to 0. Let's factor out the rho. We have rho is equal rho times rho sine squared minus cosine is equal to 0. Now the solutions of this is going to be either rho equals 0. That can't be rho equals 0, is just the origin. Okay, we're talking about a paraboloid. It's not a single point, so this can't be. What's the other thing? Well, what's the other thing? It's either rho equals 0 or rho equals, this guy's got to be equal to 0. Well, if this guy is equal to 0, throw it to the other side, rho is going to be equal to cosine phi over sine squared phi. So this is going to be the paraboloid. Next, we need to find the intersections of these guys. When do these guys intersect? So when does the paraboloid and the cylinder intersect? Well, where the formula of the formula of the cylinder was rho equals cosecant phi, and the formula of the paraboloid was rho equals cosine phi over sine squared phi. So set them equal to each other. Cosecant again is 1 over sine. So set them equal. The signs are going to cancel. You're going to have cosine over sine is equal to 1. Well, that's going to imply cosine equals to sine. So theta is going to be equal to pi over 4. Okay. Now, again, this is because it's in the first quadrant. This has a solution in the third quadrant. But since the phi is limited between 0 and pi, we don't care about the third quadrant, right? Okay. So very good. Very good. We found the angle. So again, looking at the sideways picture, what this says is, here's the paraboloid. It's inside the cylinder. Where they intersect is at phi equals pi over 4. When you go pi over 4 radians from the positive z-axis downwards, okay? Like this. This angle here is pi over 4, okay? So finally, let's try to set this up. Okay, so now, we have to be a little bit careful here. What we're going to have to do is we're going to have to calculate the area of the cylinder and then subtract the volume of the cylinder, and then we're going to have to subtract the volume of the paraboloid. The reason is this. Again, think about what you're shading with your pen when you're going from pi over 4. Well, at pi over 4 they intersected, so I have to go from pi over 4 to pi over 2. When I sweep like this from pi over 2 to pi over 2, if I go all the way out to the cylinder, then I'm going to get all these rays, right? All these rays from pi over 4 to pi over 2. I'm going to get all these rays. Now that's going to find the volume of this section, okay, this triangular section. But we need to, so from that triangular section, I need to carve out this guy. So I need to do cylinder minus I need to go out to the paraboloid. So I'm going to do the volume of the cylinder from pi over 2 to pi over 2 minus I have to subtract from it the volume of the paraboloid. So let's write down the volume of the cylinder. We know we got the equation of the cylinder was rho equals cosecant phi. So it's going to go from rho equals 0 to cosecant phi. We know that the angles are going to, this starts from pi over 4, and I'm going to sweep all the way to pi over 2. So it's going to be from pi over 4 to pi over 2. And theta is 0 to 2 pi. Rho squared sine phi d rho d phi d theta. This is standard, what you memorize. Now, this was the cylinder. Minus, we want to do the paraboloid. The paraboloid is going to go from rho equals 0 up to what was the formula of the paraboloid. We just found it on the other page. That was cosine phi over sine squared phi. I know it looks horrible. Sorry. And again, theta is going to go from, phi is going to go from pi over 4 to pi over 2, and theta is going to go from 0 to 2 pi. And, well, I didn't do it. It takes a while to do this integral. I didn't want to spend time. I just wanted to show you guys how to set it up. Hopefully you do this and you're going to again get, hopefully, pi over 2. Okay, so maybe as a homework, you guys do this and get pi over 2. Now, one thing I'd like to say is the spherical coordinate business is a lot like the polar coordinates. When you had the polar region, right? Polar region, and you wanted to sweep an area, you were trying to see how much you were sweeping, say from this angle to this angle. The integral would give you the area of this. Same thing for the polars. If you look at it from the sideways picture, again, if you sweep, it starts from pi over 4, sweep towards pi over 2, you get the cylinder, and then you need to subtract the paraboloid from it. That's how you set this integral up.